Welcome back to BrainOmega. This is NLP tutorial part 6, and we're diving into topic modeling, turning a pile of documents into a clean map of the main themes inside. We'll work in Google Colab for a smooth runtime and start by vectorizing text with Count and TF-IDF, so our algorithms have something numerical to learn from. Then we'll compare three families of approaches: NMF, fast, interpretable, and excellent on small datasets with scikit-learn; LDA, a classic, probabilistic model that often shines on medium-sized corpora via Gensim; and modern embedding-based methods, BERTopic and Top2Vec, that leverage transformer embeddings to uncover richer topics at scale. You'll see when and why to pick each method. Start with NMF for compact datasets and quick, readable topics. Try LDA when your corpus grows and you want a Bayesian view of word-topic mixtures. And reach for BERTopic or Top2Vec when you've got more data, or you already use transformer embeddings and want nuanced, semantically coherent clusters. Along the way, we'll extract top words and example documents per topic, discuss labeling tips, and show practical knobs to tune topic quality. By the end, you'll have a clear hands-on workflow for discovering themes, whether you're exploring reviews, forums, or internal text collections, and a simple playbook to choose the right tool for your dataset size. Let's get the environment ready so every library you need for topic modeling is in place. This cell installs the core stack: scikit-learn, pandas, NumPy, matplotlib for data handling, pre-processing, and basic visuals. Next, it brings in classical topic modeling tools: Gensim for algorithms like LDA and pyLDAvis pinned for interactive topic visualization. For modern embedding-driven approaches, we install sentence transformers to generate transformer embeddings, UMapLearn for dimensionality reduction, and HDBSCAN for density-based clustering. Finally, we add two turnkey libraries, BERTopic and Top2Vec, that build topics directly from embeddings, plus a specific Gensim version for compatibility. These %pip commands work smoothly in Colab cells and ensure consistent versions, so once you see installs complete, you're set to vectorize text, run NMF, LDA, and try embedding-based topic models in one notebook. We'll start by loading a manageable text corpus so we can prototype quickly and compare topic models without long runtimes. Using scikit-learn's 20 newsgroups loader, we pull a small subset of 5 categories: space, graphics, baseball, Middle East politics, and medicine, and strip headers, quotes, footers, so our models learn from the content, not email metadata. We keep both the raw texts and their labels, then wrap them in a tidy data frame with 2 columns: text, the document body, and label, a human-readable class name. This gives us a realistic, multi-topic collection that's small enough for NMF and LDA to run fast, but rich enough to showcase differences across methods. If you'd rather use your own data, you can swap in a CSV with a single text column using the provided template later in the notebook. If you want to run topic modeling on your own data, this cell shows the quickest path in Colab. Use the file picker to upload a CSV, then read it with pd.read_CSV and make sure there's a text column. Every row should be one document: a review, post, paragraph, etc. We drop missing entries with dropna subset equals text and reset the index so downstream steps don't trip over gaps, then preview a few rows with head to sanity check the content. Keep preprocessing light at first. Remove only truly empty rows. Let the vectorizers or embedding models handle casing or punctuation later. For very large files, sample a few thousand rows while you iterate, then scale up once parameters look good. If your CSV has multiple text fields, combine them, for example title plus body, into the text column before proceeding. With a clean DF text in place, you're ready to vectorize and run NMF, LDA, or embedding-based topic models. Before we feed documents into topic models, we'll do a light touch clean that keeps the words intact and the tutorial focused on modeling. The simple clean function normalizes whitespace, strips out bare URLs, they add noise but no topical meaning, and trims ends. No heavy lemmatization or stop word removal here because methods like NMF and LDA often benefit from seeing natural word forms and frequencies. We apply this to create a clean text column, then drop any rows that end up empty to avoid degenerate vectors. In a moment, we'll vectorize with both CountVectorizer and TF-IDF. As a rule of thumb, count is a common choice for LDA, which models counts probabilistically, while TF-IDF pairs nicely with NMF, which factorizes weighted features. This minimal preprocessing keeps your pipeline fast, interpretable, and easy to adapt to your own data later. Now we turn clean text into numeric features two ways, raw counts and TF-IDF weights, so our topic models have something to learn from. We configure both vectorizers with the same sensible knobs. Max features equals 20,000 to cap vocabulary size, min_df equals 2 to drop ultra-rare terms, max_df equals 0.9 to ignore words that appear in almost every document, engram range equals 1 to 2 to include both unigrams and bigrams, helpful phrases like space shuttle or graphics card, and stop words equals English to remove high-frequency filler. CountVectorizer builds a document term matrix of counts, good default for LDA, while TF-IDF vectorizer builds a weighted matrix that downweights ubiquitous terms, often a great fit for NMF. After fit transform, we get two sparse matrices, XCount and XTF-IDF, with the same shape, N documents, N features, printed at the end as a quick sanity check that our vocabulary size and corpus length look as expected. A quick rule of thumb before we pick a model, NMF tends to work best with TF-IDF features, while LDA is a probabilistic model that expects raw counts, bag of words. For small or medium-small corpora, NMF often produces clean, interpretable topics with minimal fuss. In this section, we use scikit-learn's NMF to decompose the TF-IDF matrix into two non-negative factors, W, the document topic matrix, and H, the topic term matrix. We set N components equals N topics to control how many topics we want. Seed with random state equals 42 for reproducibility. Use init equals N NDS VDA to get a good stable starting point and allow a few extra iterations. Max iter equals 400 so the factorization converges. After fitting, each row of W shows how strongly a document loads onto each topic, and each row of H, a topic vector, gives weights for terms in that topic. We then pull the top words per topic by sorting each row of H and printing the highest weight terms. This is your quick, human-readable summary of what each topic represents. If topics feel too broad, increase N topics. If they're fragmented, decrease it or tighten the vocabulary. For example, raise min_df, add bigrams. To make your NMF topics tangible, it helps to read which documents load most strongly on a given topic. The helper topdocs for topic takes the document topic matrix W, picks a topic ID, and sorts all documents by their score on that topic. It then returns the top N documents with their scores and a short snippet, first approximately 300 characters, for quick context. Printing these lets you sanity check the topic label you'd assign. Do the highest scoring docs really talk about the same theme as the top terms you saw in H? If not, you can adjust N topics, tighten the vocabulary, for example, min_df, bigrams, or try a different vectorizer. This doc level inspection is a fast way to refine topic names and spot mixed or noisy topics early. Here are a few quick tuning tips for NMF before we switch models. If topics look too broad or mixed, increase N components to get finer granularity. If they feel fragmented or repetitive, decrease it. Clean up the vocabulary by filtering very common terms with max.df and very rare terms with min.df, and experiment with n-grams. 1, 1 keeps only unigrams for crisp, distinct topics, while 1, 2 adds short phrases that can make topics more interpretable. Now let's try Latent Dirichlet Allocation LDA with Gensim, which is often a better fit for medium-sized corpora. LDA is a probabilistic model over raw counts, so we start from the CountVectorizer representation. To keep vocabularies aligned, we invert the scikit-learn vocabulary, InvaVocab, and reconstruct each document as a list of tokens present in that row of the sparse count matrix. We then build a Gensim dictionary from these token lists and convert each document to a bag of words using dictionary.doc2bo. With the corpus and dictionary ready, we train ELDA model with a target number of topics, num topics equals 10 here, set a random state for reproducibility, and use modest passes and a larger chunk size for speed. Letting alpha equals auto and ETA equals auto helps LDA adapt topic or document sparsity and word distributions automatically. Finally, we print each topic's top terms to get a quick, human-readable summary. If topics look noisy, try tweaking the number of topics, raising min.df or lowering max.df to clean the vocabulary, or increasing passes for a bit more convergence. For a deeper, more intuitive look at your LDA results, this cell spins up an interactive pyLDAvis panel right inside the notebook. Works great in Colab. The left plot, the intertopic distance map, shows topics as circles. Closer circles mean more similar topics, while larger circles indicate topics that cover more of the corpus. Click a circle to focus on one topic, and the right panel updates with a ranked bar chart of terms for that topic. The lambda slider lets you balance between raw frequency and distinctiveness. Lower lambda surfaces terms that distinguish the topic from others, while higher lambda leans toward the most frequent words. Use this view to name topics, spot overlaps, and decide whether to adjust number of topics, vocabulary filters, min.df or max.df, or passes. Note that pyLDAvis can be memory hungry on large corpora. If rendering is slow, try sampling documents or limiting the vocabulary first. A few quick pointers before you run LDA at scale. More passes and iterations can stabilize topics, though they cost time. Start with 5 to 20 topics and adjust based on coherence and redundancy. And if you're modeling domain text, consider light lemmatization and a custom stop word list to reduce clutter. For larger or more varied corpora, switch to BERTopic, which builds topics from transformer embeddings, plus UMAP for dimensionality reduction, and HDBaScan for clustering. Here we use a small fast sentence transformer, all mini LML6v2, to embed each document, then a UMAP instance with a fixed random state for reproducibility. In BERTopic, min topic size equals 10 merges tiny clusters into larger, more stable topics. Calculate probabilities equals true gives soft assignment scores, useful for ranking documents per topic, and verbose equals true prints progress so you can gauge runtime. If this cell feels slow on CPU, switch your Colab runtime to a GPU, T4 or similar, and rerun. The embedding step speeds up significantly. After fit transform, you get topics, the cluster ID per document with -1 for outliers, and probs, assignment confidences. Calling getTopicInfo returns a tidy summary table with topic IDs, sizes, and representative words. Scan the top rows to spot dominant clusters and ensure the discovered themes match your intuition. From here, you can drill into any topic to see top terms and example documents, or tweak UMAP or HDBaScan settings and min topic size to trade off granularity versus stability. Let's make the BERTopic results readable. The topic_info table lists topic IDs and sizes. We iterate over the first few and skip -1, which BERTopic reserves for outliers or noise that didn't fit any cluster. For each real topic, getTopic ID returns a list of term weight pairs, the most representative words, and their importance within that cluster. Read these like a topic label cheat sheet. The top 5 to 10 terms usually tell you exactly what the theme is. If a topic looks vague or mixed, you can increase mind topic size to merge small clusters, tweak UMAP parameters, for example nneighbors, min_dist, to change granularity, or adjust pre-processing, stop words, simple normalization. Once you're happy with the terms, jot down a short, human-readable topic name. You'll use that for dashboards and reports. To make your topics easier to read at a glance, BERTopic includes interactive Plotly visuals. This cell renders a bar chart of the top terms per topic, for the first 10 topics by default. Each bar shows a term's importance within that topic, so you can quickly sanity check labels and compare themes side by side. The chart is interactive. Hover to see exact weights, click legends to filter, and zoom if needed. If Plotly isn't available in your environment or you're missing a front end, the try except will skip gracefully so your notebook keeps running. Use this view to confirm that the top words match your intuition. If topics look noisy, revisit pre-processing, tweak mind topic size, or adjust UMAP or HDBS-CAN parameters for cleaner clusters. Top2Vec is another embedding-first approach that discovers topics without presetting K. It learns document embeddings, finds dense regions in that space, and names topics from the most representative words in each region. Because embeddings and clustering are learned jointly, it can surface coherent themes with minimal pre-processing, but it can be heavier than BERTopic depending on the embedder. In this demo, we keep things modest by slicing to approximately 1,500 documents and using the built-in Doc2Vec model with speed equals learn for a faster run. After training, getNumTopics tells you how many topics Top2Vec discovered, and getTopicsNumTopics returns the top words and their scores for each topic along with topic IDs. Printing the first few gives you an immediate sense of the clusters it found. If you want richer language understanding and have a GPU, try a stronger embedding model like use or distil use. If topics feel fragmented, reduce dataset size or switch speed settings. Evaluating topic models is part science, part judgment. There's no single accuracy number. A good approach is to mix automatic metrics with human sanity checks. Here we compute CV coherence with Gensim, which correlates reasonably well with how interpretable topics feel to humans. First, we convert our NMF output H into lists of top terms per topic. Next, we reuse the tokenized corpus, the same tokens we built from CountVectorizer, to create a Gensim dictionary and lightly trim extremes. Drop tokens that are too rare, no below, or too common, no above, to reduce noise. With topics, texts, and the dictionary in hand, coherence model, coherence equals C_V, gives a single score. Higher means the top words in each topic tend to appear together across documents. That means they cohere. Use this number to compare settings, for example, different N topics, vectorizers, or pre-processing choices, but don't rely on it alone. Pair it with a diversity check. How many unique top words across all topics? And a quick human-in-the-loop pass where you read top terms and a few top documents per topic. In many real projects, the best model is the one whose topics are both coherent and useful downstream, for example, improving a classifier or making search facets more meaningful, even if it's not the absolute winner on a single metric. Finally, let's estimate topic diversity, a quick proxy for how much your topics cover different vocabulary. We take the top terms from each topic, count how many are unique across all topics, and divide by the total number of top terms. A score near 1.0 means topics use mostly distinct words, high diversity, while lower values suggest topics share many of the same terms, possible redundancy, or poorly separated themes. Use this alongside coherence. High coherence with very low diversity can mean you've discovered the same theme multiple times. High diversity with low coherence can mean topics are distinct but mushy. To improve diversity, try fewer topics, tighten the vocabulary, MindDF, MaxDF, stop words, or adjust n-grams. To improve coherence without tanking diversity, refine pre-processing or increase n topics slightly and recheck. Here's a simple path to run this notebook on your own corpus. Upload a CSV that has at least one text column, then follow Section 1, Option B to load it, and Section 2 to do light cleaning and vectorization. From there, pick one modeling route, NMF, Section 3, LDA, Section 4, or an embedding-based method like BERTopic or Top2Vec, Sections 5 to 6, and start with sensible defaults. Tune the key knobs for your choice, the number of topics, N components for NMF, num topics for LDA, vectorizer settings, MindDF, MaxDF, n-gram range, and for embedding approaches, UMAP or HDB scan, neighbors, MINDIST, mean cluster size. When you've got a candidate, evaluate with Section 7, coherence plus diversity, skim the top words and a few top documents per topic, and iterate until the themes feel crisp and useful. A few practical gotchas to keep your results reliable. Pre-processing matters. Consider custom stop words, light lemmatization, and phrase detection, bigrams, to reduce noise without erasing meaning. Balance interpretability and coherence. Pick settings that produce topics you and stakeholders can name easily, not just the highest metric. For reproducibility, fix random seeds where possible and record library versions and parameters alongside your results. For performance, large corpora benefit from a GPU runtime and initially smaller embedding models. Scale up once your pipeline works. And finally, be thoughtful about ethics. Scan topic terms and example documents for bias, sensitive content, or privacy leaks before sharing outputs or deploying them.